Hello, this is Jack Jackson. In this video, we're going to be talking about finding volumes of solids of revolution by the cylindrical shell method. So remember in the last video, we talked about using the washer method to find a volume of a solid of revolution. And in that video, in that method, we were taking a region in the XY plane and slicing it with a little strip. We then revolved the region around a line in the plane where the strip was perpendicular to the line, or the axis of revolution. The cylindrical shell method is used when we want to find the volume of a solid of revolution where the strip is parallel to the axis of revolution. So for example, we want to revolve the region bounded by y equals 5 minus x squared and y equals x plus 3 for x in the interval -2 to 0, and we're going to revolve about the y-axis and compute the volume of the resulting solid. Now this is the same region, well, almost the same region as last time. I made it a little bit smaller, but it is the same functions. When we use the washer method, and the graph of the region and the approximating rectangles are similar to before, and so this is the picture that we have. Before we had this little area here too, but we're just going from -2 to 0, so that's the interval that we're looking at. And we're making our little strips, our rectangles, vertically. So here would be a Riemann sum rectangles for a right Riemann sum with 6 rectangles. And we're going to rotate that around the y-axis this time rather than around the x-axis. If we were going around the x-axis, we would have nice little cylindrical disc. If we go this way, we're going to have cylindrical shells going around here. So let's see what we mean by that. So instead of revolving around the x-axis, we're going to revolve around the y-axis. And I made the region a bit smaller because some of this region and this region would duplicate each other when revolving. I didn't want to mess with that. So each strip makes a cylindrical shell, and here's an application that we can see what these shells look like. Here it is here. So the idea here is that we start with a little piece here, and let's see, we want to start here. So here's our region in our XY plane, and notice we're going to start revolving that around, and it's going to trace out a cylindrical shell. Okay, notice the radius of that shell is the distance the strip is from the axis of revolution. Okay, and the height of that cylindrical shell is the height of the curve, or the height of our little strip. And the thickness is it's a real small thickness here, which is going to be our dx, our delta x. So here's a bigger one, bigger shell, and we could make that smaller and smaller and smaller. So it's moving toward an ultra thin shell as we have a delta x approaching 0. So that's what the shape looks like. For what? For one little representative piece. So it's a lot like the washer we produced earlier. I mean, really, it's more or less the same thing in one way of speaking. It's just a cylinder with a cylinder taken out of the middle. Both cases, that was the same. The difference is where the extremely small delta x is. Before, it was the height that was the delta x. So this washer became very thin, very, very thin. And the thickness was given by the length of our strip. This time, the length of our strip is the height, and the thickness, the delta x, is the thickness of the shell. So that's why we get a little bit of difference in what's going on here. So let's look at this. Let's say if we look at this radius, it says radius, but I want to think of that radius. There's actually 2 radii. There's the radius from the center line here out to the outer cylinder, the radius of the big cylinder, and then there's also the radius of the inner part that we're going to cut out. So let's let RO be the outer radius and R sub I be the inner radius. And delta X right here is that thickness RO minus RI, or delta R we might call it. Okay. Now I'm going to let just the variable r be the average of those two inner and outer radii. So here's what we get. R is r sub 0 plus r sub I divided by 2. Or another way to think of it is we let the r be the radius to the center of those, halfway between those two outer part of the shells. So it's right in the middle of it. And so the outer radius is r plus a half of delta x, and the inner radius is an r minus a half of delta x. Now, the volume then is, so we have that. So the volume is pi r square h. That's the volume of a cylinder. So for the big cylinder, that's pi r sub o square h. And the inner part that we're taking away from that is pi r sub I square h. Now, the h is the same for both, and of course pi is a constant, so I'm going to factor that out. And that leaves outer radius square minus inner radius square. Now, this is kind of cool here. R sub 0 is r plus a half delta x. The inner one is r minus a half delta x. So I'm going to be able to square this and get it in terms of r. And look what happens here. You square this, you square the first term, get that. You square the last term, you get a fourth delta x squared. Those are both positive. Multiply and double it for the middle, the half cancels, you get 2r delta x. Over here it's very similarly, r squared, you square it, you get r squared, but that minus right there makes it negative. You square the last term, which would be positive, 1/4 delta x squared, but then that minus makes it a negative. And then you multiply, which is going to give you a negative middle term, but then that negative makes it a positive middle term. Multiply and double it, you get r delta x. Now look at the r squares cancel, the 1/4 delta x squares cancel, and what you're left with is just r delta x. So we have pi h, you have two of those. You have an r delta x and another r delta x, that's 2r delta x. So you got 2r delta x times pi times h. Or I'm going to rewrite that as 2 pi r times h times delta x. Now that's the actual thing. That's dealing with the formulas of cylinders. But I think there's an easier way to think of it. The way I think of it is I think of actually taking this real thin thing. It's almost just like the label on a can, right? So you take a label on a can of vegetables or something. And if I were to cut that straight down here, straight up and down, and then, parallel to this axis, and then unroll it, what am I going to get? Well, I'm going to get a rectangle. Basically, I'm more or less going to get a rectangular prism. It's going to have a real small thickness of delta x, and then it's going to have a length times width times that small thickness would be its volume. Well, the length is the height here. Okay? The width is all the way around here, which is the circumference of that cylinder. So the circumference of a cylinder is pi times the diameter, or 2 pi times the radius. So you can think of this 2 pi r as being the circumference, h is the height, and then we just got multiplied by some thickness delta x. Either way you get it, you're going to get the volume is 2 pi r h delta x. And of course we take a Riemann sum out of that. We sum those up to get our volume approximation. Take the limit then as the delta x goes to 0 and the number of rectangles, number of shells goes to infinity. And then there's our integral. The 2 pi is a constant, so I'm bringing out front. So the volume is 2 pi times the integral from a to b of r h. I'm going to call it dr. It depends on which way the radius is going, but in our case it's dx. So if it's say you're revolving around the y-axis, the radius would just be x, assuming you're on the positive side of your region's on the positive side of the y-axis, and you revolve around. But that's just the radius, and then the height is the difference in the two curves. So here is the region we started with. So we started back here, remember, with this region, and we want to revolve that around. Okay. One thing I have to be a little careful about is because on this one, because the region is over here, the distance from the radius is the distance from one of these strips to the y-axis, which is actually the opposite of the x value here, because we're in the negative side. So it modifies this formula just slightly to be minus x there. Okay, so here's our region right here. X is this way, y is this way. Revolve it around, and we get that shape right there. Let me see if I've got that. Still got the okay, so here's another one here, another version of this where we slide around. That's showing some of the different ones there. Okay. Let's see what this one does. So again, there's another one where we're sliding, revolving around to get one particular one. Okay, so here's a view of this from a different application, different activity. But here we have the region here, revolve it around, and you can see what kind of a shape it generates. So this hole, this part down here is going to end up giving us a hole in it, kind of like a bowl. It's kind of upside down. The bowl looks like a funnel sitting on the top, just a cone right there, and then the other part is more rounded. Okay, so that's kind of what we're looking at, and I think I used a different application for this one here. There's a link to it to get this one. Okay, so now let's compute this volume. R is always the distance from the strip to the parallel axis of the revolution. Since we're on the, like I said, we're on the negative side of the y-axis, negative values for x, the R is the opposite of x to make it a positive radius. So the radius is negative x. The height of our strip is top curve minus bottom curve, which is this formula. Multiply by the negative x and we get this. The 2 pi is there. So you got 2 pi r h dr. Now dr is dx. X's are running from -2 to 0. 2 pi is there. Minus x is dr. Top curve minus bottom curve gives you the height of the strip. All right, well, pretty easy antiderivative there. 1/4 x to the 4th plus 1/3 x cubed minus x squared. Evaluate from 0 to 2. The zeros all go away here. From -2 to 0, sorry, put the zeros in there. That's that. Let's see, 4, 5 negatives, it makes a negative. 2 square, we'll cancel that 4. Then you got another 2 squares, 4 there. 3, that's 8/3. 3, 4 negatives makes positive. And 2 squares, 4, and there's 2, 3, 4 negatives is positive. So the 4's cancel, and you get 8/3 times the 2 pi is 16 pi over 3, or approximately 16.755160891. All right, here's one for you to try. Take the plane, and it's bounded by the curves y equals 3x minus x squared and y equals 0. Revolve it around the y-axis and compute the resulting volume of revolution. See if you can do it. Come back when you've done it. Press pause now. Okay, I don't have all of the illustrations here on this one, but here's the bottom line here. So it's 2 pi r and then the height. Now this curve here is hits the x-axis at 0 and at 3, 0, 0, the origin, and 3, 0, and it goes up above the x-axis in between. And the x-axis is important because y equals 0 is the x-axis. That's the bottom of it. Okay. Okay, if we go to this app here of mine, I can illustrate this with some of the strips on here too. And this is the x-axis here, so this is just 0. And we're going to go from 0 to 3 is this part up here that's bounded by them. So this is going to be 0, and B is going to be 3. So there's the shaded region. There's some of the rectangles that are in there for revolving for the Riemann sums. But this time, instead of revolving around, say, the x-axis or some horizontal line, we're going to revolve around the y-axis. So we're going to get cylindrical shells. This time, the radius is the distance for the y-axis, which is just x. And really, the height is just 3x minus x squared. Okay, so let's go back to our calculation. And so it's 2 pi, x is the radius, and then 3x minus x squared is the height, dx is the thickness, integrate from 0 to 3. 2 pi we can bring out front, distribute the x to get 3x squared minus x cubed, get an antiderivative, which is 2 pi times, let's see, x cubed, the 3's cancel, and divide by 3, that's x to the 4th, and multiply by 1/4. Evaluate from 0 to 3, 2 pi times the whole thing is 3 cubed minus 1/4, 3 to the 4th, minus, and then 0 cubed minus 1/4, 0 to the 4th. This part's 0. Both of those terms are 0. 3 cubed is 27. 3 to the 4th is 81. That's over 4 because of that. Get a common denominator. Actually, if you notice, I can actually factor out a 27 out of this. Pull a 27 out and distribute the 2. So that's 2. So if I factor out a 27, that goes out front with the pi. Distribute the 2 in, I get 2 minus a half. 2 minus 3 halves. Wait a minute, let me say it again. So if I factor 27 out, and then multiply the 2 in, I get a 2 minus 3 halves. 2 is 4 halves minus 3 halves is 1/2, and that gives me the 1/2 out here. That seems like I'm off a little bit. And yeah, that should be 27 pi over 2, but the approximation was correct at 42.411501.